So good morning, everyone. So topic for today's session is refraction through spherical surface, and it's a fairly small topic. Before this session, we had done refraction at the plane surface, and that was based on Snell's law. This also is based on Snell's law. Rather than having plane surface here, this surface is a part of a spherical, a part of a sphere of radius r, as C is the center here. So this is the radius r here. And in this case, again, what is this point? This point is taken as pole here. So pole is typically whatever surface we have, the curved surface. The physical center of that is called pole here. And if you connect pole to the center, that's our principal axis, right? So refraction at the curved surface, and we will not go into derivation. Let's understand in terms of what the formula is and how to use that formula. This is a formula on the screen, and let's understand from here. In this case, what are things which are relevant? Ray is traveling from mu1 to mu2. So this is object medium. This is image medium. So observation, this is. Second thing we can also understand, mu1 is the medium in which object is placed. Mu2 is the medium in which image is viewed from, observer is. So this is a medium where observer has to be. And so let's see that how do we apply that case here. So mu1 and mu2, this is clear. This is object medium, from medium. And this is observer medium. This is where basically refracted ray travels. This is incident ray and this is refracted ray medium. And this is normal convention. And in case of normal convention also, we need to define the origin and sign. So pole becomes the origin and the direction in which the incident ray travel. It is traveling from left to right. So accordingly, this direction becomes positive. So this is positive direction. And only thing left is R. So sign of R depends on position of the center. So this is origin, this side is positive, this side is negative. In this case, center lies on the positive side, hence R will be positive. Had the surface been concave, thus R would have become negative. Okay, and this is for object image position relationship. And in terms of magnification, if we relate magnification, there are three magnification terms we come across. We have magnification in case of mirror. Mirror was minus V by U. And in case of lens, we'll see later, magnification is V by U here. And if you look at this also, in a way it is similar. See, in case of lens formula, it is V by 1. So it is V by mu2. So the same term here comes in the similar way. Inverse of this term divided by inverse of this term. Same is the case in case of lens also. And same is the case in case of, and whatever sign we have, inverse the sign here. All three follow the same pattern. All three have the same pattern. Inverse of this term, opposite of this sign here, and divided by inverse of this term. All three cases magnifications are same. And if you want to understand how we arrive at magnification, it's very simple. So if we have this object placed on the principal axis, we can find image position based on the formula U and V. But if object is something like a lateral object placed perpendicular to principal axis, so O dash is perpendicular to principal axis, image also will form perpendicular to the principal axis. And this is I dash. And if we draw a ray from O and through pole to I dash, if this is angle of incidence, this is angle of refraction. And here, applying Snell law, we can easily arrive at ratio of Hi by Ho, which is magnification. And this is what we come to. Let's see how do we apply this into certain numericals. There's a glass hemisphere of radius 0.4 meter. So you see a glass hemisphere, and it's something like a paperweight. So many paperweights are hemispherical in shape. So this is 0.04 meter radius, and refractive index of material is 1.6. So either n or mu, I can write as 1.6 here. And place centrally over a cross mark on the paper. So assume that there's a cross mark on the paper. On top of it, you place this hemispherical glass material. You place this glass hemisphere symmetrically. So if we place it like this and when we view it from the normal position, this is is geometric center, pole. This becomes principal axis, and this is how the incident ray will travel. So this is upward is the direction in which incident ray is traveling. So this direction becomes positive. So this is origin, up direction is positive. And let's apply the formula. If I have to use the formula here, let's do that. So from is traveling from 1.6, that's a mu1. So mu1 value, it travels from medium of refractive index 1.6. Observer is in medium, to medium, which is mu is equal to 1 here. The mu2 will become 1. And how about u value here? U value is on the downward side here. This is object position. It will be negative, as is the case in all real object. U value will be equal to minus r. How about r value here? Where is this? From with respect to this point, upward is positive, downward is negative. Center of this curved surface is lying on the negative side. So we'll substitute r is equal to negative value. Let's put those values from 1.6 to 1, and u value is minus 0.04. And yeah, we substitute all the value. R also is minus 0.04. And we arrive at v value is simplified, very simple. And we arrive at v is equal to minus 0.04. And to some extent, it's a little surprising. What you find, v is same as equal to u. U is also equal to minus 0.04. Both are same. Why is that so? If you want to understand in terms of ray diagram, it's fairly simple. How do we draw the ray diagram? Typically, we draw two rays starting from object, and typically we take one ray as simplest ray, which is incident at 0 angle, and it goes undeviated. This one ray. And if I draw a second ray also, whichever ray I draw, I find since the ray start from the center, even the second ray also will have 0 angle of incidence. Hence, it will go undeviated. So what we find here, intersection point of incident rays and intersection points of refracted ray, both are same. Hence, object and image coincide. So this is something we can understand well from the ray diagram as well. Now, second part B here, curved surface is in contact with paper. We have put it upside down. Now, this glass hemisphere is placed in this fashion, and this is where the cross mark is, and we view it from a vertically above position, normal position. Now, in this case, this object, again, if we substitute here, this is, in this case, refraction was taking through curved surface. Here, refraction is taking through the plane surface. But even here also, we could have solved using plane refraction. And you notice, we have, as we mentioned earlier also, even plane reflection, we can still use r is equal to infinity. And when we take r is equal to infinity, the formula reduces to what? In that case, if I substitute r is equal to infinity, mu2 by v becomes equal to mu1 by u. That's what it becomes. And from here, again, we can easily find out. R equal to substitute in this formula, and we find v is equal to minus 0.025, which is nothing but equal to object distance 0.04 divided by refractive index, which is equal to 1.6. Let's look at one more case here. A point object O is placed in front of a glass rod having a spherical end. So this part is spherical surface. What we see as a curve is a part of a, so if we extend, it's a part of a spherical surface of radius r, and C is the center. Okay, it is placed here. What is the distance of image from pole? So what we are expecting what is image will form after one refraction. In all cases, though it is not mentioned, we always consider paraxial rays. Angle of incidence in all cases is small. The distance will not large. So let's do that here. So if we observe from somewhere within the glass, observer has to be within the glass. Then only you can see the image. But even if we do not see, mathematically we can calculate where the image will form, or where would the intersection point of refracted rays will be. That's the image position after one refraction through spherical surface. From where? Let's start from medium air. Mu1 is 1. Goes to which medium? Glass. Mu2 is equal to 1.5. How about sign convention? This is center, this is object, and this is the pole here. Which direction incident ray is traveling? From left to right. Hence, this direction is positive. Of course, a real object, u will be negative. U will be equal to minus 15 centimeter. Let's put those values. So U is minus 50 centimeter, and R value depends on position of center. This position is on the positive side. So R I will take as plus 30 centimeter, depending on the position of the center. Rest all we simply substitute the values. We find V is equal to minus 30. So image will form at a distance, which minus means what? It will form on the left hand side of the pole. And this is 15 centimeters. So if you extend this is somewhere, image will form. And let's try and understand in terms of ray diagram. How do you understand from the ray diagram? We draw two rays starting from O. So if one ray we draw at 0 angle of incidence, one ray is this incident on pole and it goes undeviated. This is one ray. And this is second ray. Though we draw like this, actually this is also a small angle. So this is a ray and this is incident here. And let's understand how this ray would be after refraction. To understand refraction, first we draw the normal. This is the angle of incidence. This is the normal here. And since it is traveling from rarer medium to denser medium, it will get refracted towards, this was a straight path. Which way it will bend? It will bend away or towards the normal. It is moving into denser medium. It will bend slightly towards the normal here, depending on what the value of mu is. So it bends something like this. So this one refracted ray, this is the second refracted ray. And if we find this intersection point, and this intersection is here, and this is happening in the virtual space. But this is a real space where real refracted rays are, virtual image will form at this point. What happens? This refractive index is 1.5. What happens if mu becomes equal to 2? As we keep increasing refractive index, this ray will bend more and more. So if we keep increasing some value of mu, it may become horizontal. What does it mean? When it becomes horizontal, image. So as we keep increasing mu, image will keep shifting further and further away. It will reach infinity. After reaching infinity, we increase value of mu even further. In that case, what will happen? It may bend down and real image may form. That's how it will depend on mu. So we are just understanding in terms of ray diagram what the effect of mu is on the image position. Okay, this is a fairly simple question, and if we read this question, we would have drawn a figure. So let's see, draw the figure here, what information is given. Let's see what this question is. A ray of light falls on a surface of spherical glass paper. This is spherical glass. This is center here. And this is the point where a ray is incident. So this is normal. And it falls on the surface, making angle alpha. So what is given here? It falls at angle alpha here. This is what is given here. And is refracted in the medium at angle beta. So this was a straight path. Let's say it gets refracted, it's moving to denser medium. So it will move towards normal. So this is a refracted path here. And what is given here? This angle is beta given. If this angle is given as beta, basically, rather given value of mu, directly angle of refraction is given. Now, and so it will get deviated. And what is asked here? The angle of deviation of emergent ray from the direction of incident ray. So this one, this is a refracted ray, it will travel in the medium. Then again, it will be incident on again this surface here. Now it will get refracted from glass to air. So again from center we connect, we draw a normal here. This become angle of incidence here. So when this was, you can very easily understand from this triangle, if this angle is beta, this angle also will be beta. And if this is angle beta here, for angle beta, this was angle corresponding angle alpha in here. So here also for beta, after refraction, this angle will be alpha. Yeah, basically two mediums, corresponding medium. So let's understand what we need to find. We need to find the angle of deviation. And just understand here, and exactly same thing we do in case of prism also. What is deviation? This was the path here. And from this path, this was the original path. Due to refraction, it has been deviated by this angle. What is the angle here? This angle is alpha minus beta. Which direction the deviation is? The deviation is in anti-clockwise direction. So deviation, refractions, and hence two deviation. First refraction, clockwise, refraction is deviation is anti-clockwise. Refraction is anti-clockwise. And what is deviation angle delta here? This is equal to alpha minus beta. Now here also, this is the path. And from this path further, it has been deviated like this. Okay, sorry, I think this angle alpha, this is the angle alpha. And if this angle alpha and this angle beta. So what is angle of deviation? This was the path before refraction, and this is the path after refraction. So this is delta 2 deviation due to second refraction. And what is delta 2? Delta 2 is again alpha minus beta. So it will suffer a anti-clockwise deviation, both the surfaces of alpha minus beta. This total deviation will become twice alpha minus beta. Okay, this is again question of refraction. One in plane surface and curved surface, and this is slightly more complex question, and this question helps you understand sign convention better. So object is piece placed at a distance r. So this is a hemispherical surface, or is a hemisphere. This is circular surface here, plane surface here. From this point pole, it is kept at distance from circular face, a semi-square piece of glass. Mu is given as 1.5. Mu is 1.5 here, and object is placed at distance r like this. Find the distance between object and image when viewed from diametrically opposite point. So if I view from here, I will view based on the rays reaching the eye. The rays which are reaching the eye, starting from here, if this object and this way the observer is, rays have to first get refracted here, and then again it has to get refracted here. It can reach only after 2 refractions. So we need to take care of 2 refractions, one on the plane surface and one on the curved surface. So let's do that one. And first refraction from the plane surface. Plane surface pretty simple. This part will become 0. So let's look at this here. First plane refraction. How is this point becomes my reference point, pole here, and this direction is positive. So if this direction positive, of course, if u is negative, minus r, I'll substitute the value. Mu1 is equal to 1, mu2 is equal to from to 1.5. This is v value, and u value is minus r. So from here, I find v is equal to 1.5 r. And let's understand in terms of ray diagram also. If I draw one ray, which is going straight like this, undeviated, and the second ray, if I draw like this here, how would this ray get refracted here? This ray here, as it enters the medium, it will bend towards normal here. If you bend slightly towards normal, if I like this is the refracted ray, and this is one ray and the second ray. So if I find the image after first refraction, intersection point of view, if I extend it back, something like this, where image gets formed, right? So this is an image. So if we get an understanding, it will be virtual image. Now, these two rays after refraction, this become incident ray for the second refraction. So as far as this spherical surface is concerned, it is only two things. Only one thing relevant is the intersection points of rays which are incident. Where is the intersection of these two rays which are incident on the spherical surface? This is the intersection point. For this spherical surface, this is the object. So image formed after first refraction becomes the object here. So let's understand here. The second refraction from the curved surface, and for this surface, this is the pole here. And pole, all the distances need to be measured from this pole to apply the formula here. And again, this direction is positive. And in terms of mu, from 1.5 to 1. So mu1 is 1.5, mu2 is 1. So yeah, mu2 is 1, mu1 is 3 by 2. What is u value here? U value has to be measured from this point here. U value will be equal to, it is 1.5 r from P1. So here from here, it would be equal to minus 1.5 r minus r. It will be minus 2.5 r. So whenever two poles are at finite distance, unless these 2 points are at negligible distance, then straight away you can take the same distance. If two poles are some distance apart, the image distance after first refraction, the value of v after first refraction is not the value of u for second refraction. When these two are not at zero distance, they are considered to be zero distance in case of thin lens. Okay, that's why they call thin lens. And r value here, r value is, to find r depends on position of center. Now, where's the center here? This is center of spherical surface, and it's on the negative side. R is -1. That's all is substitution. So all we need to understand how to calculate those values. Now we find B is equal to -10R. Basically, at this surface here, when it is incident in this surface here, we can think of again this normal direction. So this was the path here. Again, it will bend away from the normal. So again, it bends a little bit more. And if we extend this intersection point, comes equal to V is equal to -10R. -10R measured from here, measured from P2. From here, the distance is -10R. From P2, object distance is 2R. Hence, the distance between object and image is 8R. Okay, so what is important point? See, every case, whenever you apply the formula, it is all distances are measured, they are position. They are not a distance we have to use sign. So basically, U and V are object position. That's why sign are important, using the sign convention. And all are with respect to the pole. So that is something we need to be careful about. That's an important point to be understood here. That's how the rays are formed. Okay. Next question, consider a transparent hemisphere. This one n is equal to 2. In front of which a small object is placed in air. This object is placed. What should it is placed at a distance x from the curved surface? For what value of x will the final image of object will form at infinity? So question is asking what should be the value of x so that final image as seen by the observer is at infinity? That's the question. How we should solve? Again, the image also similar to previous question. This is object and this is where observer is. Two refractions will take place, one at the curved surface, one at the plane surface. Let's see, but this question is very easy to solve. See, if image forms at infinity, so how would the rays be reaching the observer, reaching the eye here? If rays will be parallel. That's what infinity means. So rays which are reaching after second refraction have to be parallel. If the rays after refraction are parallel, see, they must be parallel even before refraction. Because this is a plane surface here. So what we understand, this is an important point to understand. If the image is formed in infinity, then refracted rays must be parallel to the principal axis. So angle of refraction is 0 at this surface. That's what plane means. If angle of refraction is 0, even angle of incidence also has to be 0. That's why this rays also have to be parallel to principal axis. And if these rays are parallel, rays which are incident on the plane surface are parallel, it means after the first refraction also, the rays must be parallel. That's the condition. Or the image formed after first refraction itself has to be at infinity. And that rest all is very simple. Image formed after first refraction must be at infinity. So thus we simply substitute V is at infinity, a simple formula. And again, where are we applying? We are applying at this is surface, this is the pole here, and this direction is positive. If this direction is positive, what is the value of U? U value is negative -x. And what is the value of R? R depends on position of center. So center is on the right side, so R is positive. When we substitute, we get x is equal to R. So if we place at a distance x is equal to R, so again, try to understand here in terms of ray diagram, what would happen? See, this is the ray, how it will travel. This is the ray which is incident. If this ray is incident, this is normal. And it will bend towards normal. And since mu is pretty high, after bending, it becomes like this. That's what is happening in forming at infinity. So this question is very easy to solve and quick to solve. That's why it can come up to minus level easily. So that's all in case of refraction through spherical